So let's suppose that we're given this photosynthetic analysis question like the one I've posed here, where we're supposed to find what this pink question mark is representing. And we're given this orange product, and from this orange product, if we said that our highest priority group was the ester, then we can call this our alpha carbon, and this would be our beta carbon. And so if you remember from the claisen condensation, we were making beta keto esters. Well, this looks very similar to that. We have a beta keto, and then again we have the ester. And so it follows that rule that we have that beta keto ester, just like that, with the one small addition being that it is now cyclic. And so the claisen condensation didn't really account for that, and so a new reaction has the name for essentially what the claisen condensation is, but when you form a cyclic molecule, and that would be the Dieckmann. And so I will spell this. This is the Dieckmann condensation. Right, and so now how do we go about figuring out what that pink arrow is now? Well, we're noticing that we are forming a 5-membered chain, and so we should have 5 carbons in between our esters, and so that's your little hint if you want to go and try this on your own real quick, but if not, I'm going to start going through the mechanism. So what did I mean by 5 carbons between my esters? Well, I'm going to keep my esters the same first, so we had ethyl esters. That's just like this. Because I know where I'm going with this, I'm going to go ahead and number these carbons just so you can see where I'm talking about the 5 carbons in between. There's 1 carbon, 2, 3, 4, and this one I'm going to say is my 5th. And so I have these 5 carbons that I'm going to allow to make that ring. And so it's not completely clear how I'm going to do that. If you remember from the claisen, we're just going to follow those same rules from the claisen. And so remembering the reagents we use just some base that was some derivative from our ester. And so noticing that we have ethyl esters, I'm going to use ethanol. There's my ethanol as my solvent, and it's going to be dissolving some sodium ethoxide. Additionally, you can also use something like sodium hydride. Really just anything that will act solely as a base and not affect any other part of your synthesis. So I've listed 2 other reagents you could use, but it is often used that you use just derivatives of your ester. So going forward, sodium ethoxide has that negative charge on the oxygen, and because it has that negative charge, it's going to act like a base in this synthesis. And because it's a base, it's looking for a proton. I've just drawn in an acidic proton, and so we're going to allow the electrons from the O- to attack that proton, breaking that CH bond. When it does that, those electrons will flop down to create a new pi bond, and when it does that, it has to break the carbonyls pi bond, just like that. And so we're going to keep everything we didn't affect the same on the left. Just like this. So again, doing something with the highest energy thing in our intermediate at this point. Well, that's going to be our enolate. So our O- has that negative charge that is able to flop down. When it does that, the electrons from the CC double bond have to move through that alpha carbon and attack this new carbonyl on the other side of our molecule. And so this is like the main step that makes it the Dieckmann, because this is where we're doing intramolecular cyclization. So when we do that, we are now making a 1, 2, 3, 4, 5 carbon chain, which is what we want because our final product shows to be some cyclopentane product. And so we are most of the way there. And so let's go ahead and draw a cyclopentane just generically, just like this. We have um, a carbonyl attached to it because that was what was formed. We also have an ester, and actually I need to correct one thing. This should just be, I'm actually going to erase the whole thing. I added one too many bonds to my carbonyl. I got ahead of myself. So just like this. And that might give a hint and some insight into what happens next, right? Because again, we're going to follow the highest energy thing like we've done in the rest of this problem. And the highest energy thing now is this O minus again. And those electrons need to go down somewhere. And the place they're going to go down is just in the way to to reform the carbonyl. When you do that, you have to kick out this ethoxide. So ethoxide leaves, and we're at what looks like almost our product. And I say almost because there's that small caveat that was in the claisen condensation that we had to look out for. And that was that now we have ethoxide just floating around in solution. And this poses a small problem, easy to fix, but there is there is a proton right here that is in between two carbonyls. We know protons in between two carbonyls on an alpha carbon are very acidic, and so the ethoxide can easily pull that proton off, and it will. So when it does that, not the end of the world. The only thing we need to do to fix this is to simply add in some acid. Again, it's very similar to the claisen and the steps that we took in the claisen. So there's our ester, and we have just that minus charge. And again, acid that is strong enough to give up that proton, but not so, you don't want a weak acid, or else it will have the opportunity to pull back that proton after it gives it up, and that is counterproductive to what we want to do. So electrons to our proton, and we've arrived at our final answer. And so with all those steps, that is the entire mechanism of the Dieckmann condensation reaction.